Hello, I am Abdurrahman Barakat from the Nuclear and Radiation Engineering Department at Alexandria University, and I am with my colleagues Muharram Gaweed and Ahmad Sulaiman. My colleagues and I have been concerned about the importance of safety in the nuclear and radiation field. So we have thought, why couldn't we put our fingerprint in such an important domain that may evolve the industry into the next level? So we have thought of a composite detector that can determine the amount of neutrons produced from a fission chain reaction to give data enough to control the fission rate. Let's dive deep a little bit. When a neutron hits a barrier, it's not 100% guaranteed to reflect back as a pole would because it doesn't obey classical mechanics. It has quantum properties where its behaviors are different. Interestingly enough, the neutron may pass through the barrier and appear on the other side. And here comes our calculations. We have used the equation of transmission probability of a neutron to determine how probable a neutron will pass through our composite. Since transmission probability depends on the kinetic energy carried by the neutron, we had to calculate it too, but that was just the calculations for a single neutron, and millions of neutrons are produced during the fission reactions. So we have moved to calculating the number of atoms in an M mass to know how many neutrons are produced from atoms present in this certain mass. To simplify our calculations, we have considered an assumption, which is that every reaction in the fission chain has in its product 3 neutrons every time it occurs. This assumption was attempted to allow us to express the number of neutrons produced from the fission chain in the form of a mathematical series formula, so that we can calculate them a little bit easier. And now, we have got the total number of neutrons and the probability of their transmission across the barrier, and by multiplying these two numbers by each other, we will get the number of neutrons that will transmit through the barrier. Now let's talk about how it could actually impact our real life positively and make a difference in our daily life. The benefits of our barrier technique can go beyond being used in the safety of nuclear power plants. It may evolve medical imaging devices like SPECT and PET devices, which are currently used to detect malignant tumors. It has vast applications in radiation-related fields, including industrial applications, radiation detection and measurement systems, radiation therapy techniques, and the development of a new method in the process of calibration radiation-based devices. And that was our research and idea. Thank you for your attention.